So, how will be corrected the statement? Yet, if the initial state is mean zero, you have convergence to what we proved yesterday, which is a gauge invariant state. Now, let us see what happens if the initial state is non-zero. You see, you still have a Gaussian structure, which is characterized by the fact that a typical Gaussian structure on the Weil algebra, we have the spin Weil operators and the spin vacuum vector. The expectation of the product of spin Weil operator now we want to prove that converges to the limit expectation. The vacuum will go into some vector on the Weil star algebra. In some particular case, this will be Fock state. But in general, we want to show that this vector, this state on the Weil star algebra is more general. And in fact, what we find in the limit is the exponential of a quadratic form. This is a minus jumped here. Of a quadratic, there should be minus here and minus here. A quadratic form in which you see there appear the two non-gauge invariant terms corresponding to the plus plus and minus minus. In fact, the covariance is this, where S bar now is the mean. In the central limit theorem, you have to deal with centered random variable. So you have to subtract the mean. And so S bar is the expectation, the E0 expectation of S plus. Okay? And similarly for S minus. So you have four possibilities for the covariance. And all four a priori, because you see, it is true that for example, say take S minus, S minus. S minus will go to zero, but there are the cross terms, which may not be zero. Depends very much on the state that we are on this E0. Remember, E0 is a state on the 2 by 2 matrices. So what we do is, I recall what we did yesterday, because the first part of the proof is the same, and all the discussion today is to show where the non-mean zero assumption plays a role. So the expectation of the spin Weil operator is a spin. The Weil operator are product of identical copies of a single spin 1/2 Weil operator. And the product goes from 1 to k. So, since E0 to the power tensor power n is a product state, this expectation is simply reduced to a power of the product of the expectations of the single Weil operator. And now we use the approximation. You see, yesterday we computed that the Weil operator for a given with a given argument z has this form: a scalar term which goes like cosinus, and an operator term which goes like sinus, because the normalization disappears, because here we have a quotient. So only the phase of the complex number remains. So remember, by definition, this probably I don't draw it right, but by definition, my z is E(I) alpha j mod z j. So when I have only, because we will then reformulate the product and work only with the zj, forget the phases. Okay? So now you see what we want to do is that we want to reduce everything to mean zero. So let us introduce the mean value of S plus S minus for the zero state. So this is S plus and minus are 2 by 2 matrices, and the S bar plus, S bar minus are numbers, in general, complex numbers, so modulus less or equal than 1. So we simply, from the expression that we had before of the Weil operator, we will add and subtract the mean value. So the cosinus term is scalar and remains the same. Here you have mean zero element, and what we have, the correction is simply a scalar term. But now notice that this scalar term is of the order of sinus of z over square root of n. And we will take n go to infinity. So this will asymptotically have the behavior of 1 over square root of n for uniformly bounded z. So we can rewrite this for z in a bounded set. We can rewrite this as the corrected Weil operators plus a term which will become negligible. Then, therefore, when we pass from, this is true for a single Weil operator, but we have a product of such operators, okay? So this product, when we subtract the mean, will give rise to a factor which is now inside the product, a factor of the order 1 over square root of n. However, what is the first remark? The first remark is that, you see, these quantities, we have these operators, and let me call fj the first term. So we have a product of the type f and j, and plus something, which is of order 1 over square root of n. It is clear that if the f and j are in norm uniformly bounded, this product will be of the form of this form, where, remember, this is an operator, and for an operator, O of 1 over square root of n means that the norm of this operator is less or equal than a constant times the 1 over square root of n. You see, and this is clear because only the first term is the dominating one, and all the remaining term contain at least one of these factors. And so the smallest degree will be this one. All the other one will decay much more rapidly. So the order of magnitude is 1 over n. Okay. In our case, the constant c is equal to 4 because f and j is this expression. Cosinus is less than 1. And these operators have norm less or equal than 1. This is an operator. This is a number. I mean, and in any case, less than 1, so we have less than 4. And obviously, the condition is satisfied. So now we have this quantity, and we can neglect this factor because we are interested in the limit of products of this. Again, we will apply the same argument. Okay. So now we will expand the Weil operators as we did yesterday, and we expanded the cosinus and sinus, and we now, however, we are with our operators, which I have introduced as tilde, which are the centered, which means with the mean subtracted. This is the only difference with what happened yesterday. Okay? So now we essentially approximate sinus at first order and cosinus at second order, and we obtain this asymptotic expansion where this is the cosinus term, this is the sinus term. and then we have the product. Now, again, we have here expanding the product. This is what we did here. Expanding this product, 1 will go to 1. This term is already of order 1 over n, so it can only be multiplied by 1. And therefore, the sum will arise, because each of the j will be multiplied by 1 and give rise to a sum. And the similar here. Here, however, I can multiply by 1 or by itself, as we did yesterday. And it appears this term, which now is mean 0, so, and this term, which has not been 0, because it's a covariance. When we will take expectation, we get covariance. And the term that remains is of this order, as we explained before. Now, let us expand. We have found in the terms of the product of two mean zero terms, it appears this expression. So it is convenient to put it together, separating the, putting together again the S plus with the is mean 0. You exploit the fact now. You simply do this product and collect the terms which have the same z, So you see that you have 4 possibilities corresponding to the 4 terms of the covariance. When we will take expectations, the 4 terms of the covariance will come out from this. So the term with both z will correspond to plus plus, and this term will correspond to plus minus, and so we have z conjugate. This will have z conjugate, z is minus plus, and this is minus minus. So now we take expectation, and now we can say that the term of order 1 over square root of n disappears. So we obtain this asymptotic for the single product. See, that we write in more compact form, taking expectation and using the covariance. And this term is negligible. Because when we take now the full expectation of the product of n Weyl operator, which live on the tensor product of n copies of the 2 by 2 matrices, they will give rise to this product. We have already estimated this product. Now, the only difference is that the power n appears, because all the factors are identical, corresponding to the identically distributed independent random variable. Okay? So, using this expectation that we have taken before, we obtain now this limit, and this goes to what we said in the limit. This will be 1 minus 1 over n times something to the power n, which, when n goes to infinity, will converge to the exponential of quadratic form, which characterizes Gaussian expectation. You see, here the minus sign is correct, because there is minus here. And, well, again, there is an because then should be minus here. But the minus sign is minus 1 is correct. Okay, so this is what I wanted to show, that when you subtract the mean, apparently this fact, this innocent fact, has a non-trivial consequence on the type of Gaussian states that can be that can come out. Okay, now we go to the lecture of today. Lecture of today will have to do with so imagine that you now want to pass from 2, which is a very special dimension, so from C2 to arbitrary C to the power D. I want to illustrate this technique. This was used many years ago in a paper that we did with Bach, Alexander Bach, in the very early 80s. And we use a trick. The trick is interesting because it will help understand better the nature of Fock space. It requires some introduction on representation theory, some known elementary fact in the representation of the rotation group that I want to recall. So what we do is this. We take a space, we have a d-dimensional space, and our idea is the following. Instead of redoing all the calculation and all the estimates, we reduce a d-dimensional space to a certain product of two-dimensional spaces. Why certain product? Of course, it cannot be a usual product because we are not saying that D is a power of 2. But what we do is different. We take the D-level system, which means C to the power D, and we exploit the fact that C to the power D is isomorphic to the symmetric tensor product of C2. D minus 1 copies of C2. This helps you to understand the emergence of the number operator. Remember, the philosophy of these lectures are how, from the Bernoulli process, the boson standard structure emerges canonically. Okay? And so let me recall now how this embedding works and why you obtain an isomorphism. Remember that the symmetric tensor product of D minus 1 copies of C2 is the subspace of the full tensor product generated by the homogeneous element. We already met this in our previous lectures. I repeat just for completeness. And the scalar product is not this one, the natural one. Okay. Now, let us introduce the canonical basis in C2. This is an orthonormal basis of C2. And we form the symmetric tensor product. You see, this symmetric tensor product are labeled by the index k. And k goes from 0 to 1. And what is the physical interpretation of this symmetric tensor product? This means simply that there are in this okay. You see, this corresponds to the spin number vectors. Why number vectors? Because the parameter k labels how many spins are in the state E2 and how many spins are in the state E1. Okay? And this is why d minus 1, because 0 is allowed. Let us calculate the norm of this vector. I did the calculation because we used a reference book, which is the very famous book making this analogy between spin and boson. It's called a book by Bidenan and Luke, which appeared in the Encyclopedia of Mathematics of Addison and Wesley. I have put the reference. And we discovered that there is a kind of small computational error in the normalization of the spin number vectors. So I did the computation in all details, even if they are a little bit boring, so that when you read the lectures, you can check that the correction to this famous textbook is correct. So this is what I did. I want to compute the norm of this vector. This is a symmetric tensor product. So because of symmetrization, and symmetrization is a projection, the symmetrization projection means that I can apply it only on one side because of the projection property. It's a self-adjoint projection. So if I do the scalar product of two symmetric things, I can consider one non-symmetric times the symmetric one. Now, the symmetric one means that I perform all possible permutation of the indices, and then I sum and I normalize by the number of permutations. Now, we have this is the standard product, scalar product. So what we have is this. We have single out the first factor, the factor containing E1, and then there will be how many factors containing E1? Since we are in this vector, there are exactly d minus 1 minus k factor containing d1, and k factor containing E1, and k factor containing E2. So whenever the permutation P1 gives rise to a 2, this will be 0. And this will be non-zero if and only if P1 will be equal to 1. And similarly for P2. So in total, how many? We have this n factorial must be d minus 1 factorial, obviously. N is d minus 1. We are now in d minus 1 dimension. Okay, so this is the correct form here. We have d minus 1 vector, and the permutation that leave invariant the fixed points of E1, the fixed position of E1, are this, and the permutation that leave invariant the fixed position of E2 are this. So you get exactly the inverse of the binomial coefficient. Therefore, the natural normalization will be to multiply by the inverse of this square root. And this is why it appears the square root normalization of the spin number vector. You see? From this, okay. Now, we want to, I have collected in a single lemma all what we need concerning representation of SO3. Remember that when we take the products of Weyl operator in a tensor product, we obtain an exponential of a sum. That is how these operators come out, from products of Weyl operators. This will be from the products of the number operator, but I have not yet discussed the number operator, okay? I will do later on. So, what I want to prove is this. Remember, the vectors that I call phi d minus 1k are these ones, the normalized symmetrized tensor products of the vectors of the basis in dimension d minus 1. So these are the spin number vectors. So what I want to prove is that the spin number vectors play the analog role of the fundamental basis in the two-dimensional case. Well, since we are in d dimension, here we have that these are not eigenvectors of S+, but they behave like a finite number operator. I go from number k to number k plus 1. Remember, k is the number of E2 states, of the upper state, not ground state. Similarly, S minus up to a multiplicative factor. This is the multiplicative factor that we have corrected. In the Biedermann, look, the denominator is in the numerator. And we think that the correct expression is in the denominator. So we have this. And S3, these number vectors are eigenvalues of the n number vector, as you would expect. Okay? This is a self-adjoint operator. It generates an abelian subalgebra, which in the language of Lie algebra is called the Cartan subalgebra of this representation. Because in a moment we will prove that this algebra is, in fact, from this you see immediately that this algebra, the algebra generated by S3, is a maximal abelian subalgebra, because the spectrum is non-degenerate. And this is a basis of eigenvector. So it has a non-degenerate spectrum, and therefore the abelian algebra generated by it is maximal. So now we have these identities. I want to compute this factor, projections. You see, and this computation is done by exploiting the symmetrization operator. Symmetrization means, now is correct normalization, d minus 1 factorial. The symmetrization is simply what we said before. The only difference is that now I am applying, remember, J, H of S plus are the natural embedding into the tensor product. So JH of any operator X will be X embedded into the factor H times the identity on the index set minus the factor H. So this is what we have also denoted last time, like 1 over H complement. Because the index set is fixed in our scheme of infinite. Remember, this is an element of the infinite tensor, infinite or finite, depending on V, of M2. Matrices. Okay. So now, you remember that the action of S plus is 0 if the index is 1. And this rising, this is the rising operator. So if the index is 1, it will give 2. If the index is 2, it will give 0. Okay? So only for 1 it will survive. And the sum will be contributed only by this. But E1 will be flipped into E2. So when we sum over all possible H, see, this doesn't depend on H. It's constant, so I can bring outside. I will obtain, again, this comes from the symmetrization, from the previous result, and I will obtain this result. As you see, when I sum over all H, this reproduces all possible permutations. And so this reproduces the symmetrization operator, but the vector now has changed. That is why I put E prime. Because E prime, this, before I had D minus 1 minus K ground states and K upper state. But now I act on one of the ground state with the plus. And so I have K plus 1 upper states and D minus K minus 2 lower states. So now I obtain this. And this is by definition the new factor. This is, now I remember the appropriate normalization for this vector is not the same as this, because I have 1 K plus and 1 2 plus and 1 ground level minus. So I multiply and divide by this. And this gives me exactly this multiplicative factor. So you see, from this, I did pedantically all the steps to show that the factor should be this one. Okay? So we obtained that the action of the rising operator, of the collective rising operator, increases the K by 1 up to a multiple, which is this one. Now, similarly, we do exactly the similar thing for S minus, only that we find now a different normalization factor, because S minus will decrease by 1. So I am now in the tensor product with only K minus 1 factors equal to the upper level, and 1 plus in the lower level. So I have this different factor which arises, just the computation is similar to before. With S3, the difference is the following, that S3 applied to J, remember S3 is the Pauli matrix, in fact is 1/2 of it, but we can say that S3 is 1, 0, 0, minus 1. Okay, so when I apply to the upper level, it gives plus, and lower level gives minus. That is why when I apply the S3 to this factor, this will come up. So if JP is 2, it will be plus 1. And if JP is 1, it will be minus 1. Well, in fact, I wrote the other convention, in fact, with the calculation I did. In fact, I am using this. Just a moment. No, it's correct, because remember, E2 is upper state, and the E1 is lower state. So it's correct. This is correct. Okay. So you see now, when I sum over all possible H, the only dependence on H remained is here. So I have to sum this minus, and this is exactly the difference between the number of states in upper level and the number of states in the lower level, which is exactly this one. So that is how it comes, the factor 2k plus 1, and not the factor that is in Biedermann and Luck, which is only, there is not this 2 and there is the other sign. You see, it is natural that the number operator, because we are not speaking of states, so it is quite this. There will be representations, as I told you, in which the number operator is unbounded below. I gave you the example of the equilibrium, Gibbs states. Okay, And from central limit theorem, you couldn't obtain if you have only a positive number operator with positive spectrum. So this is reasonably, this is correct to have both positive and negative values for the spin number operator. Okay. Now we want to prove that the collective operators are a representation of the Lie algebra at one level. Remember, the Lie algebra S of SO3 has generators. The Lie algebra SO3R has generators that we can take. Here we are taking sigma plus, sigma minus, and sigma 3. Equivalently, one can take sigma 1, sigma 2, and sigma 3, the Pauli matrices. You see, sigma plus and sigma minus are the analog of creation and annihilation. Sigma 1 and sigma 2 are the analog of P, position, and momentum operator. And so here I did the calculation with the generator plus minus 3. And you see, the fundamental point about tensor products is that for different h and k, this commute. So the commutator is 0. And only equals survive. And then it becomes, this sum is not an homomorphism of star algebras. But, fortunately for us, is an homomorphism of starly algebras. Okay? And we exploit this property. So this is, the commutator gives twice sigma 3, which is exactly we are using the commutation relation, if I remember well, and no, yes. No. I think it is. I think this is the correct commutation. No, because no. I have no. It's correct. I have this. Because you see, no, sigma 1. The product of sigma plus and sigma 3 is a projection. And the same for sigma 1. And this is a projection exactly of sigma 3. So here it is twice sigma 3. The other one was wrong. This is correct. Sigma plus minus sigma 3 is minus plus sigma minus plus. I have to correct this. Sorry, I forgot. This is to be correct. Okay. So, I mean, independently of the details, the important point is that the collective operators have the same commutation relation of the 2 by 2 matrix, of the single spin 1/2. Okay? And so from these two identities we deduce that it is a representation of Lie algebra. It's also a representation of star Lie algebra because the adjoint of sigma plus is sigma minus and sigma 3 is self-adjoint. As I said, S3 has a simple spectrum. Therefore, now we want to prove, this is a known fact, that this representation of the Lie algebra SO3, so SO3 is 2 by 2 matrices, but we have a representation in the 2 to the power n times 2 to the power n matrices, because we are in the tensor product space. Okay, this is famous the D representation, or D divided 1/2 represent D minus 1 divided 2 representation. So what I want to prove, that this representation is irreducible. Irreducible means that there are no invariant subspace. If there is an invariant subspace, since this is a star subset, so generates a star algebra, then the orthogonal projection of this subspace must be in the commutant of the representation. So to prove that the representation is irreducible, I have to prove that the commutant of the representation is trivial. Okay? The proof is simple. I gave you because it's a known fact, but it's all very often quoted. But it is worth to see the proof because these objects are very important in applications. So we do in 2 steps. The first step is that we have already seen that the algebra, abelian algebra, Cartan subalgebra generated by S3 is maximal, because the spectrum is non-degenerate and it is full a full basis of eigenvector. Okay, so it's maximal. Now, what does it mean to be in the commutant of the representation? To be in the commutant of the representation means to be in the commutant of these 3 operators, which are the generators of the representation. It's an if and only if condition. So it must be in the commutant of this. And of course, the commutant of this is contained in the commutant of only S3. But we know that this is just S3 closure, which means that necessarily, since S is maximal, if an element is in the commutant of the representation, it will be in a function of S3. But I know, so this is what I prove here, that it must be a function of S3. This follows from maximality. However, if I have a function of S3, let us take an arbitrary function of S3, then S plus will act, if I consider S plus F3, there is this symbol should be erased, it is a misprint. The correct form is after, you see. I am computing the commutator between F3 and S plus. And my goal is to prove that this is different from 0. So this is what I want to prove. That FS3 commutator with S plus is sufficient, is non-zero. So this excludes, unless Fs3 is the constant function, so is a multiple of the identity. Of course, this is always in the algebra. Okay? So I want to prove that if this commutator cannot be 0, therefore it means that only the multiple of the identity can be in this commutant, and therefore the representation is irreducible. And the reason is simple, because we have proved that the number operator, so I am computing now S plus F3. If I apply F3, I remain in the same number, is an eigenvector. It will be F of the eigenvector that we know is 2k plus 1 minus d. Then I apply S here. And now we know that S plus increases k by 1. And so I will have a certain factor. If I apply the converse, I have now increased by 1. Again, there is phi d is repeated twice. This is one of the two has to be erased. So I increase by 1, and after that I apply S3. So the factor will be different. here unfortunately is not seen very well, but what will be different will be only, this is the same. What will be different will be this factor, because F3 here is applied to K, and here it is applied to K plus 1. Okay? Since this factor is the same, I conclude, unfortunately, you cannot see in the transparency because it is covered, it's cut. But what I have proved is that we have to have that f of this eigenvalue of f2 plus 1 minus d, f2 k plus 1 minus d, must be equal to f of 2k plus 1 minus d plus 1, which is the one coming from the second. Okay? So this must be true for every k, and therefore f must be constant. And therefore is a multiple of the identity. Okay? And this proves that effectively the representation is irreducible. So the fact is important because it means that not only we have an isomorphism of Lie algebra level, but we have also an isomorphism, when we make this identification, of CD identified with the C2 power tensor symmetric D minus 1, also the linear operators on this become identified with the linear. So we have a full identification not only of spaces but also of algebras using a that is why the irreducibility is interesting for us. It's not homomorphism, but they are linearly isomorphic. Okay. Now we have made the preparation of what we want to prove. Now we want to generalize. Now you remember I wanted to say that we have the emergence not only of the Gaussian inside the quantum, but in the Gaussian central limit theorem we also include Poisson. Why? And you can begin to see the root of this if you look at the d copies of the spin-Weil operators. If you look at the d copies of the spin-Weil operators, they are tensor product of copies of the single Weil operator, which has this form. We have computed that, just a moment, I want to do first at operator level, then we will act on the vector. But it gives more insight to look more generally at the operator level. So we have this tensor product, which we can write as a usual product using the J embeddings. Because instead of writing always tensor product, is more suitable because we work in a single algebra. And we don't have to write a huge number of tensor symbols. So I have rewritten in the language of the J using the other notation that we introduced yesterday, which is the following notation. If I have an operator, for example, J, for example, S plus S minus, and I embed with the kth embedding, I will use the notation S plus R minus K. And sometimes, unfortunately, I have written like this, with the index up and in the index. I hope you forgive this discrepancy of notation. So, for example, here is with the index down. So now you see, with this notation, the tensor product becomes a standard product. So I can deal, and all the variables, the operators for different h, commute. And this is a scalar which commutes with everything. So I can perform this, what is morally a tensor product. Again, this has been cut. But, okay, maybe it is convenient that I write on the blackboard what is this factor. You see, what is the argument that brings this factor? And this product will be exactly this one. This product that you cannot see there will be the product for M going from 1 to J of these operators corresponding to Z divided modulus Z of S plus HM minus Z bar divided modulus Z S minus HM, the same. Okay. This is just a standard combinatorial argument, because if I must take this product for a k from 0 to d minus 1, and how many factors will come? If I take d minus j minus 1 factor of cosinus, which correspond to the identity, the operators that remains are exactly j. Okay? But they can be everywhere in the factor of the tensor product. That is why this function h comes out. hm means where I pick up this operator. Okay? And do you understand now that whenever I pick up this operator, there will be a sign, but sign will not depend on h, and this is a scalar. And so I bring out the sign here. Okay? So you begin to see that because we are now in, if we parameterize the cosinus of z like a complex square root of some probability, then the sinus will be the complex square root of another complex square root, not necessarily, of the complement. Okay? And then you begin to recognize the binomial, how it comes binomial distribution, and you know very well that in rescaled central limit theorem, the limit of binomial will give Poisson. This is the logic. Okay? I think details I will give you next time. Details are important because Poisson, as you know, is the distribution of the after the limit. You are in the boson space, and the Poisson distribution is precisely the distribution of the number operator in the exponential vectors. Not in the vacuum. Vacuum is trivial, it's constant. But in the exponential vector. So we want to, this will come out from central limit theorems. Okay? Maybe rather than the details, in the next time, maybe, because these are rather technical details, but I wanted to really to show that when we speak of quantum central limit theorem, the structure is enormously more rich than classical. In classical, you only have convergence to a single distribution. I told you already several times, but it's very important because it's one of the crucial points of quantum probability. A single quantum central limit theorem is in fact a multiplicity of central limit theorems, depending on how you adjust the states. And this case, which is the Moivre-Laplace, is the simplest possible context in which you can concretely see how this philosophy is concretely realized. Okay?